Okay, we also did problems where we were talking about decreasing the momentum, unlike the golf ball, which was at rest when we hit it with a force. This is the opposite, where we have an object in motion already, like a car that has a certain velocity and then it has a certain mass, so it's got a certain momentum, and we crash into two objects. In this case, the sort of extreme examples would be a brick wall or a haystack. A brick wall, of course, means you're going to come to a stop very quickly and your impact time will be very short. And a haystack, which would obviously have some more give to it and would increase your impact time, thereby reducing your impact force. But let's do this let's do this out here and see what we get. All right, first off, just like the other impulse problem we did, we want to find out what the PI and PF are. So the initial momentum here is going to be what the car had in terms of mass and velocity combined at the start of this problem. So here we would say the car was traveling at 5 meters per second and it has a mass of 500 kilograms. So 500 kilograms times 5 meters per second equals 2,500 kilogram meters per second. All right, that's the initial momentum. Final is going to be what the momentum of this car is after it's hit the brick wall. And its velocity is going to be 0, so if you multiply anything times 0, you're going to get a final momentum of 0. So what's the impulse? Delta MV equals PF minus PI. We're talking about a PF now of being 0 minus 2,500 kilogram meters per second. That's going to be negative 2,500 kilogram meters per second. All right, so there's your impulse. Okay, now is that impulse going to be different for the car that hits the haystack? Well, does it have the same initial mass and velocity? Yes. So its initial momentum is also going to be 2,500. But what about its final momentum? Well, it hits the haystack and it does stop. So its final momentum would be 0 also. So the impulse here, the change in momentum, delta MV, is the same in both of these cases for both cars. And that's what it is. Okay, there's the impulse. But let's go further and let's say that over here, the time of impact, the time it took for that car to get from going 5 meters per second to 0 was, I don't know, 0.01 seconds, all right? Whereas down here, let's say the car took 2 seconds to do that, to come to a complete stop. Well, now we're going to include this equation here, delta MV equals force times time, and we're going to do out in each case what the overall impact force would be. And you know just from your own experience, if you were driving in a car and you were going to crash into something and you had a choice of a brick wall and a haystack, you'd probably steer toward the haystack because you're going to have less force exerted on you by the haystack than by the brick wall. And the reason for that is because the impact time is short, thereby increasing the impact force, whereas down here the impact time is long, thereby decreasing the impact force, but the overall impulse, the change in momentum, is the same for both cars. This is just like that watermelon example where we drop one off the diving board, we drop one onto the deck and one in the water. The impulse is the same, the time of impact and the force of impact are what vary. Okay, so for the the car that hits the brick wall, the impulse is negative 2,500. I'm going to run out of room here. That's going to equal force times 0.01, which is, we're going to divide by 0.01. That force is going to equal negative 250, 25, let's see, 250,000 newtons. So over here, the force of impact, 250,000 newtons. Yikes, don't want to be in that car. How about for the haystack? MV equals force times, in this case we said 2 seconds was the impact time. So again, I'm probably off the screen here, but delta MV is 2,500. That's the impulse. Kilogram meters per second, divide that by 2, we're going to get 1,250 newtons. 1,250 newtons. Would you rather be in a car that hits and has 1,250 newtons of force or 250,000 newtons? I want to be in this car. I'm steering for that haystack every time.